Okay, physics and equilibrium. So equilibrium is a really interesting case of where forces are balanced, and it helps us to really figure out all sorts of things because it tells us a lot about what's happening in two dimensions all at once. So let me talk you through a few examples of equilibrium. So equilibrium means that there is no acceleration that is being experienced. So it doesn't mean it's stationary. It means that there's no accelerations to be experienced. So obviously, if I have something that's stationary, say I have a box sitting on something, so that's going to be an equilibrium. And also, if I have something that's moving, if this box is moving at a constant velocity, or if I have a car that's moving at constant velocity, it means it's at equilibrium. I can have things that are falling as well. So I can have, parachutish, a skydiver who's in a parachute, right? And there's my skydiver, right? And here's his parachute. And he gets to terminal velocity, right? He's still falling. Well, without a parachute, you're going to fall at, what is it, like almost 95 miles an hour? And that will stay steady, meaning that the forces are balanced. You're no longer accelerating. So this is a key thing that you want to get. So equilibrium means that all my forces balance, or we'll say it this way mathematically, the sum of the forces are equal to 0. But it doesn't mean just in one dimension, though. This means this must be true in two dimensions. So it's really handy. This is what we're going to be able to do. So we'll be using the same equation in two dimensions to figure everything out. So there's a series of steps we go through, and we're solving these that makes it a little bit easier to deal with. But really, what I'm going to do is I'm going to make a free body diagram, say what forces are interacting with something. I'm going to add up the forces and say that some of the forces in my x dimension need to add up to 0. I'm going to say that some of the forces in my y dimension need to add up to 0. And then when I do that, if I'm careful about the signs, say this is positive and this is positive, if I'm careful about the signs of those forces, then everything will work out. Let me go through a couple examples to show you what this can look like. So first example, so I'm going to have a box hanging from here, and I want to know what are the tension in the two strings there. So let me call this T1 and T2. So I want to know what are the tensions that they're holding up this box. So first step I'm going to do is I'm going to draw a free body diagram. I'm going to be careful about this. I don't want to draw a free body diagram with components at this point. I just want to draw the forces I know about. So I have two things touching it. So I have a string going in this way. I'll call this T1. I have a string going in that way. I'll call that T2. And those are the only contact forces on the box. I do have a field force, so acting at a distance, I have gravity is pulling it down. And you can write it a couple of ways. You can just write force of gravity, and sometimes we're going to write this mg. We'll get into this in a little bit, why that is. But it's a handy way of writing the force of gravity. So you might see either one. They're giving me a value for this, right? So I might put in here the value for this, and I want to know these two. They're giving me some angles as well. It's kind of tricky, right? So I have things going off at angles, and if I can get them separated into components, then I can sum the forces in the x and the y, and that's what I'm going to do. So they're telling me about this triangle, so I'll just sort one since it's the same on both sides. So here's T1. They tell me this has an angle of 53.13 in here. 13. So I'm going to separate this into T1 in the y direction and T1 in the x direction. And let me calculate this, right? So T1 in the x direction, right, is going to be T1 times the cosine of the angle. Right, it's adjacent here, and this is going to be T1 times the sine of the angle. So I'm going to do this for both of these, really. And so I'm going to write a second force diagram, a free body diagram. So I'm a second free body diagram. So I'm going to line things up and break things up into components. This is still the force of gravity acting here, but now I'm going to have T1 that's going horizontally here. So this is cosine theta. I'm going to have T1 times the sine of theta. So I've broken T1 into components. Notice I'm still, I haven't drawn them way out in space, so I've drawn them right next to each other coming off of my object here, and my object is now a dot. Because the angle is the same on the other side, I end up having the same thing. So I'm going to have T2 cosine theta and T2 cosine theta here as well. So now I have something I can make sense of. So I have horizontal and vertical forces. So I'm going to say, well, let's call this positive, and let's call this positive, to the right positive. So this is going to be a positive, and this is going to be a negative force. So now when I sum my forces, so I'm going to sum up my forces. In the x direction, that's going to be 0. So when I sum up the forces in my x direction, I'm going to have T1 cosine theta positive, and I'm going to have this one T2 cosine theta going in the opposite direction, which is going to be negative. So these add up to 0, which means these are equal, right? And hopefully that makes sense to you, right? So my horizontal forces here must balance, so it's not so helpful. Really, I can't use that mathematically, but some of the forces in the y dimension, now that's a little bit more helpful, right? So now I have my positive forces pulling up. So I'm going to have T1 sine theta pulling up plus T2 sine theta pulling up, and I have my force of gravity pulling down, and I'll put in a number here. This is 80 newtons. Right. I could use a system of equations, so I have two equations and two unknowns to try to get there. It's a lot easier in this case to look at this and see this is symmetrical, so those two forces must be the same. So the weight of this box, the weight of the 80 newtons, is being shared equally amongst these two wires. So I'll just call T1 and T2 the same. So this is my tension, whatever that is. It's going to be of sine theta plus that tension times the sine theta minus 80 equals 0. And now it's just math, right? So I'll move my 80 across. One of these plus one of those makes two of them. So I'll have 2t sine theta is equal to 80, or t sine theta is equal to 40, or t is equal to 40 over sine theta. And now I get my calculator out and get to an answer from that. And I trust you to do that. So one example of how to use these, but the idea is the same, right? So I'm going to go through the same steps. So I'm going to draw a free body diagram. A free body diagram does not have components. Do not draw components down here. You get marked wrong if that's you're asked to draw a free body diagram. I'm going to draw a second one that has components now separated out into the x and y dimension. And then I can sum the forces in my x, sum the forces in my y, and then math. And that should get you there. I'll go through a couple of more complex ones, and hope that's helpful. Talk to you soon. Bye.